In this video, we are going to solve the problem count inversions. Let's read the problem statement and understand what we have to do in this problem. Problem says that we'll be given an array of integers and we have to find the number of inversions in the array. Now, two elements, ARR of I and ARR of j, form an inversion if the ith element is greater than the jth element and the ith element is on the left side of the array and the jth element is on the right side. So inversion for an array indicates how far or how close the array is from being sorted. For example, if the inversion value is 0, this means that already the array is sorted. But for the case of reverse sorted array, the inversion count is the maximum here. Let's understand this through some examples here. Suppose that if I have an array which is something like this. Let's say if I have an array which has got elements, let's say 7, 8, and then after that I have got 12 here. Now if you see here, the condition says that there should be a particular ith element on the left side that is greater than a jth element belonging to the right side. But if you see for the test case that I have taken, there is no ith element that is greater than the jth element on the right side. Okay, so if you see this I and this j, always remember that I should be less than j. If you see this I and this j, so this ith element is not greater than the j, not greater than the jth. Then if I check this jth element also, so ith element is not greater. Okay. Then after this, if you check this as the ith element and this as the jth element, again ith is not greater than the jth. So this is why you can say that the count of inversions will come out as 0 for this particular array here. So the inversion count for such an array is basically 0 when the array is already sorted. But suppose that if I had an array which was something like this. Let's say if I had 9 and then after that I had 2 and then I had 4 here. Now if you see this particular array here, so we have to observe that 9 that is there, this particular ith element, it is greater than 2 as well as it is greater than 4. So this particular ith element is greater than both these elements belonging to the right side of the array. So that is why this will be counted. So how many counts I can have here? 2, because 9 is greater than 2. I have one pair 9 comma 2, another pair 9 comma 4 here. Now after this, what will happen is if you will put your I index at the element 2 and j will be here. Now this is not an inversion because the ith element is not greater, so will not count. So you can see for this test case the inversions were 2. Now suppose that if you had an array which was in decreasing order, now what will happen here? Suppose that if I had an array like 5, 4, let's take some other elements here. Suppose that if I had what? If I had 10, then I had something like let's say 5, then I had 3, then I had something like 2, and then I had 1 here. Suppose this is the array which is in decreasing order, that is the reverse sorted order. Okay, now what will happen here is if you see this 10, it will have inversions with this and this element, all the elements basically, right? So answer will be updated to what? Initially it will be 4 plus, if you see when you go to this element 5, so it is greater than which elements? 3, 2 and 1. So plus 3 will be done here. Okay, then after that when you go to this particular element, that is let's say 3, then it is greater than 2 other elements on the right side. Correct. So 2 more will be added. And then after that, if you go to this particular element 2, so you can observe that it is greater than this particular element 1. So we need to add one more. Now if you add this up, what is the count that you get? 4 plus 3 plus 2 plus 1. This comes out as nothing but 10 here. Okay, because the sum of the inversions is 10 here. Now after this, if you observe, so what can I conclude? If the array is sorted in the decreasing order, then I can conclude that for the very first element, there are n minus 1 elements on the right side. So you can say that there are n minus 1 elements on the right side. Okay, then for the next element, that is this particular element, how many elements are there on the right side? If they are all smaller, then the inversion count will be n minus 2 for this element. Then similarly for the next element, for this particular element, the elements are these, right? So the inversion count will be n minus 3 here, because if I'm at a particular element, then all, like if I was at 10 suppose, then the elements, assuming that all the elements on the right side are lesser here because the array is sorted in decreasing order, so that is why the inversion count with respect to 10 would be n minus 1. Then I'll check for other elements. So for 5 the inversion count would be n minus 2, then for the next it would be n minus 3 up till you reach 1. If you see the sum of this particular series, this is basically a arithmetic progression. So the sum of this series would be n into n minus 1 divided by 2 here. So I hope this makes sense, right? So so what happens is, for an array which is sorted in the decreasing order, inversion count is maximum possible, and this can be n into n minus 1 by 2 here. I hope you have understood this. Now let's understand how we can do it in a brute force fashion. So as I had already did a dry run, but still let's see what is the brute force approach. So basically you can do what? You can basically traverse throughout the array, and for every index you can find the number of the elements that are smaller on the right side. Okay, so basically for a particular ith element, let's say you are at this particular ith element, so you can try to find that how many elements, how many indexes are there, j indexes, that are having elements lesser than the ith element. Those will be counted in terms of inversions. Okay, so let's see the with the help of this dry run. So you can observe here that whenever I'll be at a particular index, I'll check all the elements on the right side. So you can see that in the worst case, what I'm doing is for one particular element, I'm checking all the remaining elements on the right side. So for one element, for one ith index, I'm checking n minus 1 elements. So for n indexes, I would be checking n into n minus 1, which is roughly n square. So that is why the complexity for this approach would be n square, because we are trying to check all the possible pairs here. Okay, what will happen here is, firstly your I will be starting here. Firstly your I will be starting here, and then your j will be starting from I plus 1. So j will be here. Since the ith element is greater than the jth, so you'll count. Then after that j will move here. Again ith element is greater. Then after that j will move here. Again ith element is greater. So that is why the inversion count with respect to the element 4 will be 3 here. Now after that, next time what will happen? My I index will move forward. The moment it moves forward, so I is standing at the element 3 and j will be standing here. Now ith element is greater, again j will move. Now ith element is again greater, so the count increases by 2 more. Then after this, what happens? When I am at this particular element, that is 2, then my j will be standing here only. Now is the ith element greater than jth? Yes, so the count will increase by 1 more. And after that, if you see for the last element, there will be no inversion count, because for the last element there are no elements on the right side, so the counter will be 0 only. If you see the total sum comes out as 6 here. So this is what you can define as inversion. Okay, now since we applied the brute force approach, so this would take order of n square time, because for every ith element we are checking all the elements on the right side. So we are checking all the j elements on the right side, that is starting from I plus 1 index till the end of the array. Okay, if you will see here, what we will do here is we'll basically take the length of the array. Okay, that is n. Then after that, inversion count variable is there. We'll iterate in the array. Why we are iterating one less? Because if you see for the last element, there will be no inversion, because if I'm at the last element, so for the last element there are no elements on the right side. That is why we can run the I loop till less than n minus 1. Then we'll iterate for all the indexes from I plus 1 till the end of the array. Okay, and for a particular ith element, we'll check all the elements, j elements on the right side. And if there is any ith element for which the jth element is lesser, and the ith element is basically greater than the jth element, then you will increase the inversion count variable, and at the end you will return the counter. This would take order of n square time, because we are using two loops. So this would take n square time, because we are using nested loops here. Now how can we improve this? In order to improve this, we can use the merge sort concept here. Okay, the idea will be that we'll be choosing for a particular array, we'll be choosing a midpoint, we'll be dividing the array into two halves, and obviously the left half will get sorted, the right half will also get sorted, and then we will basically try to merge both the sorted arrays. But here, apart from applying the merge sort, we will also try to count the number of inversions using basic intuition here. So that I'll try to explain using the dry run. So if you see, let's read this. It says that we can use merge sort to count the number of inversions. Firstly, you divide the array into two halves, left and the right. That is what we do in terms of merge sort as well. Now after that, we can count the inversions in both the halves. Now what does this mean? Suppose that you had this whole array here. Now what you do is you divide this array into two halves, and then after that you process the left half. So basically, obviously you'll be sorting the left half, you'll be sorting the right half. While you are doing that, like, you will basically be able to count the number of inversions in the left half as well as the right half. Understand that what does recursion do? The task of recursion is to solve a smaller problem. So like, what will happen is, initially you had the whole array, you divided it into two halves. So for this array, the same process will be applied, and for this right array also same process will be applied. Now inversion count for the left half and the right half would be done. After that, what you have to do is you have to finally merge both the sorted arrays. So what you can see here is we also count how many elements from the left array are greater than the elements on the right array, as they represent the cross inversion. Because see, there will be three types of inversions here. The thing is that once you have divided the array into two halves, okay, then what will happen? Some inversions will be lying in this left array where a particular element x is greater than y. Okay, some inversions would be there because of this right array where x would be greater than y. But like, some inversions will be, see, understand one thing. if there is a particular inversion pair, let's say x comma y, where x is greater than y, so the thing is that there can be three possible scenarios. What are those three scenarios? Both x and y lie in the left half, both x and y lie in the right half, or what can happen is x lies in the left half and y lies in the right half. So what I'm saying is, when you will divide the array and you will like sorting will be done on the left array and the right array, you'll be able to count the number of inversions in the left half. You'll be able to count the number of inversions in the right half as well, because you'll be solving a smaller problem. But when you are merging, then the last scenario where one element x is lying in the left array and y is lying in the right array, that would help you to identify the number of inversions here. So basically, in terms of implementation, the merge sort function that we used to write, the merge function that we used to write, in that we have to make some manipulations such that we can count the pairs where x is lying in the left half and y is lying in the right half, because all the other pairs where x and y are in the same half, that will be counted using the smaller problem. So if you see here, what will happen is, let's say if you had a particular array, you will break it down into two halves. Now what will happen is, obviously, what does the merge sort do after that? It will sort this particular array and it will sort the right array also. Now once they are sorted, so basically the number of inversions in them will be counted respectively in the smaller problem concept. But the thing is that when you are merging, so one element x lying in the left half, another element y lying in the right half, such that x is greater than y, so those will be the cross inversions that you always want to count, because element from the left half is greater than the element from the right half during this process. So we will keep a track of that. Now what do I mean by this? So if you see here, firstly let's have a look at the count inversion function. So as I said, suppose if you have an array from a particular L index till the R index, okay, and if the left range is lesser than the right, this means that we can divide the array into two halves. Suppose this is L, this is R, we'll find the midpoint, okay, and we'll try to divide this particular array. And you know that like once we found out the midpoint, then we divide the array into two halves. What happens is, we apply the same approach on the left half from L till M, and on the right half from M plus 1 till the end of the array. So that is what we are trying to do. We are trying to call the count inversion function, because we are trying to sort, as well as we'll be trying to sort and count the number of inversions in the left half. Okay, and we'll try to sort and count the number of inversions in the right half. After that is done, once the left half and the right half have got sorted, then there will be an element x, there will be an element y. X will be lying in the left half, y will be lying in the right half, such that x comma y make an inversion pair such that x is greater than y. So we have to count them. So for this we have this count and merge function. This count and merge function will be same as the merge function in a normal merge sort. This will help us to count the number of inversions very easily and efficiently also, because earlier in the brute force approach we were checking all the possible pairs here. That was n square approach. But here, with the help of sorting, we'll be able to count the number of pairs much easier without checking all the pairs individually. Okay, how can we do that? So if you see here, count and merge function. So obviously, like n1 and n2 is the size of the arrays that you have, and then after that, if you see, left array will be there and right array will be there. Now after that, what we will try to do is, we'll have a resultant variable that will be initially pointing to the, so result will be calculating the total number of inversions. I will be standing at the beginning of the first array, j will be standing at the beginning of the second sorted array, and k will be standing here at L. Okay, then what will happen here is, we'll iterate, and you know that there are two conditions while we merge. Since there are two arrays, left and the right array, so if the element of the left array is lesser than the element of the right array, then there is no problem. Then we'll do what? Then we'll simply update the kth element to the left element, and then we'll increase the I pointer. But otherwise, if the right element is lesser, then that is when we have problem, because you have to understand one thing, that if you consider left half and right half, and there is a particular element x here, y here, if x is greater than y, because basically the else part is what? When the right element is what? Else part is when the right element is basically lesser. Okay, whenever the right element is lesser, then there will be inversion. So we will be cleverly counting those inversions. How? Let's have an understanding with the help of test cases here. So suppose that if you have this particular array here, suppose that you had this array, like this whole array was there, but you broke it down into two parts, okay, and now you have to merge it. So what you can see here is that one I pointer would be standing here and another j pointer is standing here. My resultant variable right now is equal to 0. So I'll have this array. Now, is the ith element lesser than the jth element? Yes. If the ith element is lesser than the jth element, if the element of the left array is lesser than the element of the right array, I'm completely okay with it. So what I'll do is, I'll update this element 2 here. Then what will happen now? Next, we will say that I pointer will move forward, so I pointer will come here and J pointer will stand here. Now what will happen is I pointer that is there, okay, it is pointing at an element which is greater than the jth element. So this means what? After this, if you'll see, so right now the ith element is greater than the jth element. This means that element of the left array is greater than the element of the right array. What does this mean? This indicates that 5 is greater than 3. Okay, if 5 is greater than 3 and the array is sorted, left array is sorted, obviously right array is also sorted. 5 is greater than 3, then 8 will also be greater than 3 and 11 will also be greater than 3. Okay, so understand one thing, that if the size of the first array is 4, then how many elements I can, how many pairs I can count all together? I don't need to individually check the pair 5 3 8 3 and 11 3. If 5 is greater than 3, all the elements on the right of 5 will also be greater than 3. So all this can be counted. How? If n1 is equal to what? 4, and the I index is standing at 1 here. So how many elements are there? Total 3 elements are there that are greater than 3. Okay. So 5 comma, you can understand 5 comma 3 pair is there. Okay. 8 comma 3 pair is there, and then 11 comma 3 pair is there. Correct. So 3 elements are there. How can I count this? So for in my result variable, always what I need to do is I need to do result plus is equal to n1 minus I. When will I do this? Whenever the element in the left array is greater than the element of the right array. That is when I need to count inversion. So n1 minus I here. Size of the first array minus I here. So what will happen is here initially the result will be updated with 3 here. Why? Because you can observe that n1 is 4, I is standing at 1. So total you have 3 pairs. So n1 minus I will give me 3 here. So the result will be updated with 3. Then after that what will happen? My j index will move forward after putting the element in the final array. So 6 will like 3 will be here. Now if you see, the left element is lesser. So if the left element is lesser, then we can simply put the left element and we can move forward. Whenever the left element is greater, then that is when we want to count. So if you see, I will be standing here. Now what happens here is, when my I point is standing here and j point is standing here, is the ith element greater than the jth element? Yes, it is. So if 8 is greater than 6, understand this thing, that if 8 is greater than 6, okay, 8 can make a pair with 6. 8 can, like 11 can also make a pair with 6. So if 8 is greater than 6, all the other elements on the right of 8 will also be greater. So how many elements are there in total? n1 minus I, because n1 is 4, I is at 2. So 4 minus 2 is what? 2. So you will add how much? You will add 2 more. So every time you have to add n1 minus I whenever the ith element of the left array is greater than the jth element of the right array, because this is basically, you can understand, the left array and this is the right array. Now what will happen next? We'll process this element 6 inside the array. Okay, then after this my pointer would move forward, so j will be standing here. Now since the ith element is lesser, so I have no issues. I'll put 8 inside this particular array. Okay, then my I pointer will move forward. Now if you see this particular ith element, it is greater than the jth element, and all the elements on the right of this ith element will also be greater than the jth element. But since there is only there is only one element, so 11 comma 9 pair, you can understand, will be there. So the number of elements will be like the number of inversion pairs will be n1 minus I. So n1 minus 3 will be 4 minus 3 will be 1 here. So you'll add one more to this, and this will be basically total 6. The result will update to what? 6 here. Okay. Now after this, what will happen? Since my jth element was lesser, so 9 will be updated in the array, and then my j will move forward. Now my ith element is lesser, so 11 will be updated here, and then after that I will move forward, and then j will be processed. So 13 will be processed, and you can see inversion count for the left right array comes out as 6 here. Total 6 pairs are there. So this is how, while merging, we are able to count the number of inversions. So you can understand that what we did was, we broke the problem into smaller problems. So basically, whatever array we have been given, understand this fact, whatever array we have been given, our task is to divide that array into two halves. Now for this half, we'll call the count inversion function. For this half also, we'll call the count inversion function. So basically the sorting will be done on the left half and the right half. Okay, now there will be one scenario when x is greater than y and both the elements are lying in the left half. Another scenario when x is greater than y, both are lying in the right half. But one scenario will be when so these two scenarios will be counted when you will call these functions, right? But the thing is that when x is standing, when your x element is standing in the left array and y element is standing in the right array, okay, so then also you need to count inversions. So for that, when you're merging both the arrays, then you can count such inversions efficiently. So you can understand that how we are able to count the pairs, or how we are able to count the inversion pairs easily without checking each and every pair individually. So that is why, instead of having n square complexity. We are having n log n complexity because we are using the internal working or the functioning or the merge function of the merge sort concept. After that, you can see again, like we find the n1 and n2, the count in both the subarrays, and then left and right arrays. After that, the result was 0, I was 0, j was 0, and k was initialized. Then after that, we check if the left array is lesser than the element of the right array. I don't have any issues. Update the left element and then do I plus plus. But if the left element is basically greater than the right element, then this should be counted in terms of inversion. So we should count the number of inversion pairs as n1 minus I here. That is what I have explained. And we keep on moving our j pointer and k pointer respectively. Now, whatever remaining elements are there either in the first array or second array, we basically merge them also. Okay, then at the end we return the merged array, which is basically overall sorted here. Now, if you see, this would take how much time? Since we are only applying the concept of sorting, so that is why merge sorting, in fact. So time complexity would be order of n log n because we are not taking any more time than n log n for sorting purpose. And the space complexity would be basically order of n because obviously you can understand that we are using the concept of arrays here, and internally when we apply merge sort, so it takes order of n space here. Now let's try and see the final code for this as well. So I've written the code. Let's try and submit this now. So you can see that my code got accepted. I hope that you're clear with this concept of count inversions. Basically, initially what we have done is we have this function where we are calling the count inversion from the 0th index till the last element of the array. And then count inversion is doing the same thing. And then after that, we have implemented the count and merge function, which is the implementation of merge two arrays concept in the merge sort only. But we have increased one functionality where whenever the left element is greater than the right element, then we are counting the inversion pairs very easily here. So that is why time complexity improves for the count of inversions here. So I hope you have understood this. Make sure to mention in the comments. Thank you for watching this video.